Hello everyone, welcome to my YouTube channel. In this video, I am going to show you how to perform molecular docking using Autodock Vina. In my last video, I explained how to use Autodock 4 for molecular docking. But Autodock Vina is faster than the Autodock 4, and some literature suggests that its coding function is also better than Autodock 4. That's why it is used more in different molecular docking studies than the Autodock 4. In this docking experiment, I am going to use lactate dehydrogenase A as protein molecule and darunavir, one antiviral drug, as ligand molecule. The PDB-ID of the lactate dehydrogenase A is 4QOH. Okay, and as requirement, we we are going to require MGL tool or Autodock tool, which is a protein and ligand processing tool. So this MGL tool is also used in case of Autodock 4, you know, but after processing or preparation of the ligand molecule and protein molecule, finally the docking is performed through Vina or Autodock 4. So the up to first stage, that means preparation of protein ligand, is done through MGL tool or Autodock tool. Second step, that means during molecular docking, Autodock 4 can be accessed through Autodock tool. So if you have not watched my previous video on Autodock 4, I suggest first you watch this video, then you will get some idea about the molecular docking. But in case of Vina, we can't access the Vina through the Autodock tool. So separate command line can be used to access this Vina docking software. But the first stage can be done through Autodock tool. Okay. So let's move to the molecular docking. Initially, I am going to show you the protein lactate dehydrogenase A through a visualization software, that means BioVia Discovery Studio. And some detail about the protein, you can get it from the RCSB protein data bank. So this is the PDB ID 4QOH. Okay, so this is the associated paper where the authors have designed a synthetic inhibitor of lactate dehydrogenase A, and the IC50 value of this inhibitor is 1.7 micromolar. So we can use this inhibitor as control, or through this inhibitor we can identify the active site pocket of the protein molecule. Okay, so you can see this is the structure of that synthetic inhibitor. This is 3,6U, and this is the NADH which is required for its activity. Okay, and few other chemical compounds which is associated with this protein ligand complex, and these ions or chemical compounds are required for crystallization. So first download this protein ligand complex from the protein data bank, download PDB format, and after downloading you have to open it in a visualization software, that means BioVia Discovery Studio. So I have already opened it in BioVia Discovery Studio. This is the protein ligand complex. Okay, so now hit on hierarchy. So you can see this is a tetrameric protein containing 4 chains: chain A, chain B, chain C, and chain D. So we can retain only one chain because the active site is present in each subunit. The protein is tetrameric, that means the protein has 4 active sites or 4 binding sites. Okay, and in chain A, the 3,6U, this is the synthetic inhibitor, is present in chain A. This is the 360. It is present within the active site. So for molecular docking, we need only these chains because I am going to perform within these active site pockets. So let's remove the other chains and the water molecules and the other associated ions, but I am only retaining the synthetic chemical compound which is present within the active site pocket of chain A. Okay, you can see. So now we can locate the position of active site. So this information will help us shortly for the designing the grid. Okay, grid box. We are going to create a grid box around this known synthetic inhibitor, and this is the ligand molecule which we are going to dock within the active site pocket of LDHA. So I am copying its coordinates and pasting it within the hierarchy of lactate dehydrogenase. Now you can see this is the test chemical compound, and this is present outside of the protein active site. And through molecular docking software, we will dock or we will check the pose, possible binding pose of this test molecule within the active site pocket of the lactate dehydrogenase. So we can process this protein molecule through BioVia Discovery Studio. It's a visualization software as well as protein processing software, and we can also use Autodock tool. So I am opening Autodock tool for the processing of protein and ligand molecules. Okay. So first, create a folder in your desktop, and I have created it, and the name of this folder is docking folder. Okay, and within this folder keep your protein and ligand molecule. Now I am opening the Autodock tool. It's already installed in my laptop. Okay, so Autodock tool has opened. Now load your protein molecule. So this is the protein molecule in PDB format, and left side this is the hierarchy of the protein molecule, and we are going to retain only the chain A. Okay, so select chain B, C and D. Now go to edit, delete selected atom. So chain B, C and D will be deleted. So now only chain A is present, and now delete all the water molecules. Edit, delete, delete water. So all the water molecules will be deleted. Then let's see what are the other chemical compounds or ions which are present with the protein molecule. So up to phenylalanine 331, these are the amino acid. Then NADH, sulfate ion, and one other chemical compound, and this is the synthetic inhibitor. Okay, so select all these, or first time retain this synthetic inhibitor. It will help us for designing the grid. Okay, so I am not deleting now. It's edit, delete selected atom. Okay, now go to grid, macromolecule, choose, select macromolecule or protein molecule. So I am saving it in PDB-QT format. The protein is now saved in PDB-QT format. Then grid, set the grid box. You can see this is the position of the grid box. Now you can highlight the non-synthetic inhibitor, and you can see the grid box is present outside of the non-synthetic inhibitor. So first of all we have to cover this ligand molecule, because this is the active site. These amino acids, they are the active site residues. So let's move this grid box, change the center coordinates, x, y, z coordinates of this grid box, and place it in a way so that it can cover the non-synthetic inhibitor. The non-synthetic inhibitor is present now within this box. That means the active site pocket is now covered with this grid box. Okay. And now file, output, grid dimension file. Save it. I am saving it in my docking folder which is present on desktop with the name of grid.txt text format. Now you can see within docking folder a grid file is present containing the information about the grid. This is the center coordinate and this is the x, y and z dimension. Okay, here through Vina Discovery Studio we can also get information about the active site pocket and we can also design the grid box. Okay, but in case of Vina Discovery Studio the grid box is spherical in shape, not like the cubical which is present in the Autodock tool. So first select the ligand molecule. I have selected 3,6E and then click on define ligand to select the ligand molecule. Okay, then click on this define and edit binding site. Select from current selection. That means I have selected synthetic inhibitor 3,6E. So from current selection. Now we can see a grid box or a spherical grid is now present surrounding this non-synthetic inhibitor. You can also increase the size or expand the size, and you can also get the information about this grid from here. Click on it and then attributes of the SVD site here, and now you can get the information of the grid center coordinate and the radius. Because it's a spherical grid, so no x, y, z dimension will be there, only the radius of this spherical grid. Okay, you can also save this information from here. Okay, so up to this step we only extracted the grid information through two different ways, that means using Autodock tool and using Vina Discovery Studio. Now let's finish the protein and ligand processing step. Okay, so first of all remove the known inhibitor from the active site pocket because this region should be empty to dock new ligands into this active site pocket. Okay, select, then edit, delete selected atoms. Now add the polar hydrogen, add, and these steps are same while doing protein processing for Autodock 4. Then atom assign AD4 type, add charges, Coleman charges. Okay, so the protein processing is finished. Now save it in PDBQT format. Save, write, PDBQT. So location is already docking folder and I am saving it in PDBQT format. The protein is now saved. Now ligand, input, open. So ligand is present in PDB file. So choose PDB, select darunavir, open. So ligand is now open. Torsion tree, choose root, ligand torsion tree, detect root. You see this is the ligand. Then save this ligand in PDBQT format. So name of this ligand is darunavir dot PDBQT. So now both processed protein and ligand is now present in this docking folder in Autodock format. Okay, PDBQT file and the protein in Autodock format. We need these two input files for our docking. We need another thing, that is one a text file containing the different parameters for molecular docking using Vina. So this file is known as configuration file and we have to generate this configuration file in a simple text file. So I have already generated a blank configuration file, and then I have to only write the name of the protein file, that means 4q08 pdbqt, in the name of the ligand darunavir.pdbqt. Okay, and output is out.pdbqt. Then we have to add the coordinates information, that means center coordinates and size of the grid. So we have already extracted the grid information, so let's copy this grid information from this grid file. So in grid text file you can see here are grid information. So the x, y and z dimension are 40, 40, 40, and these are the center coordinates. One important thing is that in case of Autodock, the grid spacing is 0.375, but in Autodock Vina, grid spacing is 1 angstrom. That is the difference between the Autodock and Autodock Vina. Okay, so if we change this spacing from 0.375 to 1, then the box will increase in size. So uh, let's move with it. We are not changing this dimension. Okay, so we are retaining this dimension. That means center x, copy the center x from here. This is center coordinates of x, y center coordinates, and z center coordinates, and dimension I'm keeping it 40, 40 and 40. We may reduce it to 20 because the spacing will be more, 1 angstrom, so we can also reduce it to 20. That's enough. And exhaustiveness at 8. Okay, so this is our configuration file. So file, save. So our configuration file is now ready. It's present in desktop. I am copying it and pasting it to the docking folder. So configuration file is now present within this docking folder, and two input file, protein input file and ligand input file. If you have not installed Autodock Vina, then for installing type in Google Autodock Vina, then go to Autodock Vina Deep Research Institute. Okay, download. For Windows version, click here. Software is downloading. Double click to install the software. I agree. So the software is installing now. Okay, the software is now installed. So after installing the software, the executive files will be present in the C drive. Okay, within C drive, the Script Research Institute, where the Autodock is installed. Okay, then you enter into the Vina folder and you will find three executable files. So copy this executable file and paste it to the docking folder. So now these executables or the applications are present also within this docking folder. Now we have to access this application through command line prompt. For that, enter here, type here command prompt. Now go to the folder where the executable files are present. That means this docking folder. So click here and copy the path of this folder. Copy, and in command prompt type cd, that means change directory, and right click. So this is the path. then enter. So now we are in this docking folder, within this docking folder. Okay, now through a command we can run the Vina docking software. Okay, for that command is, now type vina.exe. That means I am calling Vina application for molecular docking. Then space double hyphen configuration .txt. This is the input file, but from where the molecular docking software will read the different parameters and inputs and will write a log file. That means the result file. So log.txt. Okay, then enter. You can see the Vina is running, and Vina will give us total 9 outputs. That means base 9 poses we will get from the docking using Autodock Vina, and their score will also be presented here, and it will also be written in this log file. And all these poses, base 9 poses, and this log file, the scores will be automatically saved in the default folder. Here default folder is the docking folder. Okay, our docking is now finished. You can see here the result output. So we have obtained 9 poses, and these are the scores of the different poses. The first pose has highest score -8.2. So delta G value kilocalorie per mole is -8.2. Then rest of the pose are lower in their score. Okay, so these poses already have been saved in the docking folder. So this is the protein chain, single subunit, and these are the poses. Okay, first pose, second pose, third pose, fourth, fifth, sixth, seventh, eighth, and ninth. These are the 9 poses. Okay, so we can also visualize the interaction of this pose with the protein. So I'm copying the coordinates and pasting it to the hierarchy of protein. So now you can see this ligand molecule is present within the active site pocket. But earlier it was present outside of the protein. That means due to docking, now this ligand has moved into the active site pocket, and this is the base pose as per the Vina docking software. And now you can visualize the interaction, or you can analyze the result. Okay, and the scores has been saved in a log file. So this is the log file. You can see these are the score of different poses. Okay, and also the RMSD, lower bound, upper bound. So what is RMSD? In next tutorial or in subsequent tutorial I will explain what is RMSD, and I will explain several other things, how to visualize the interaction using different visualization software. Okay, so that's all for today's tutorial. Thank you for watching.